Yeah, so like I said, I'm Tyler, and I'm going to be talking about, mainly how we are using Cutlass, which is an NVIDIA library, or really less of a library and more of a, kind of collection of modular routines that you can like assemble to create linear algebra operations, and how we use that to get high performance quantized inference in vLLM. So yeah, and I want to start out with like what we're gonna do, what we're not gonna do, just to kind of like set expectations. So we're gonna motivate, why we do activation quantization in vLLM, and we're gonna be talking about some fundamentals of performance in order to, kind of justify that sort of, we on like firm theoretical grounds, because I think that's important. So we're gonna be talking about compute and data movement there. We're going to be talking about speeding up linear layers. So that's dense gems for the most part in this case, using Cutlass. We're going to walk through the linear algebra of how to handle scales and 0 points that arise in quantization. Scales are easy. 0 points are kind of a little less easy, but Cutlass makes them a little easier. We're not going to be talking about like really ultra low precision quantization. We'll flash some performance numbers, but we're really talking about, W8, A8. So 8-bit weights, 8-bit activations. We're not talking about like 4-bit weights or going even lower than that. We're not going to discuss how to quantize LLMs. We're going to assume that somebody's already quantized them for us and they've handed them to us. We're also not going to be delving into the inner workings of Cutlass main loops or layouts, mainly because I'm really not an expert of that. I'm more of a user of Cutlass here, and so we're really talking about kind of like systemically vLLM and how that relates to Cutlass. We're also not going to talk about quantized attention, mainly because vLLM doesn't really support quantized attention yet. That's future work. I only have about 14 slides, and I usually budget, about a minute per slide. So we can kind of slow down, and if people want to kind of discuss what we're going through, I think we can do that. And then like some of the plots are a little, maybe not what people are used to seeing. So we can, kind of slow down and talk through those. Right. So yeah, let's get started. So yeah, we're talking about quantizing linear layers, where we really spend the majority of the time. One caveat there is, as the context length becomes larger, the time we spend in attention becomes, starts to dominate. You can sort of start to see this on the right plot where, okay, so let me slow down and walk you through this one. So this is a breakdown of the individual layers in Meta Llama 3 8B. And we're comparing both FP16 and FP8. And so this is like kind of maybe hard to see. The taller ones, the relatively taller ones are FP16. So it goes FP16, FP8, FP16, FP8. And the first thing you'll probably notice here is the wide swaths of pink. So the pink layers are the dense gems, the linear layers. And you'll also notice that that's the main difference between the FP16 and FP8 charts, is that that's really the only thing we've sped up. Some other interesting things here. So red is attention. So as we go from left to right, we have more, and we have like a larger batch size. And so attention actually becomes more expensive than, like, relatively more expensive than gems. Basically because gems become cheaper as the batch size. The linear layers become cheaper as you increase the batch size. attention doesn't. And we're going to be talking, that's actually going to be like a major like thing that we cover in this talk is like why the gems become kind of like relatively more efficient as you increase the batch size. So yeah, one other thing of note, the sort of like green layers these are the quantize operations. And so we have a work in progress to kind of delete the cost of the quantize operations by fusing them onto other operations. So you can fuse, there's sort of like, there'll be 4 quantize operations per layer of a transformer. 2 of them can be fused onto, an RMS norm operation. One of them can get fused onto a CLU and mul operation. The other one's a little harder to fuse. You have to fuse it onto attention itself.
You gotta give it to me. Just get me out.
So we're working on a torch.compile based system to kind of delete the costs of these and fuse them away. Yeah, so I think that's like, hopefully gives you kind of like some motivation. We're trying to speed up the biggest cost here. One other notable thing is that this is just model execution. So we're not measuring a lot of the overheads from the server, anything that like kind of is around, we're not talking about like processing inputs, detokenization, that kind of thing. And the reason I say this is because all of the overheads that we've eliminated over the past couple of weeks in vLLM will make quantization, like the effects of quantization, pop out that much more, which is great. Okay, so we're talking about INT8 and FP8. Primarily INT8 we use on Ampere because Ampere doesn't support FP8 computation, and we mostly talk about FP8 on Hopper because FP8 is honestly very great. There's a few different kinds of quantization we'll be covering. So per tensor, where an entire activation or entire weight tensor is quantized using the same scale and 0 point, and per token and per channel you'll have like a vector where every token in your activation tensor will have a different scale and maybe 0 point, and then per channel quantization is when every output channel in your weight matrix will have a different scale and 0 point. And then finally, we'll talk about, symmetric versus asymmetric quantization. This is just if you have a 0 point or not. The 0 point is, if you have a distribution that's not centered around 0, then you can get up to an extra bit of precision if you have a 0 point. But it also adds a bit of complexity, which we'll talk about as well. All right. So yeah, we're talking about linear layers in vLLM. And these are GEMS. So GEMS stands for General Matrix Multiply. So we're not talking about MOE models here. Although many of the same kind of factors apply, MOE models they'll have a lower arithmetic intensity, and you'll know what that means in a couple of slides. But yeah, so we're talking about dense gems. And so on the right here is a figure of a gem, which is is what we execute in a vLLM linear layer. So in this, we have a large weight matrix, typically. So large is for llama 8B, 4096 by 4096 at least, and up to, maybe 4096 by 26672. So there's actually 4 sizes of gems that we execute, at least for N and K. And then the other dimension, M is the number of tokens that we're processing in the linear layer at once. That's smaller and variable. And also when I talk about M, this is like a flattened number of tokens. So, as you increase the batch size during decode, that will be M. But then we can also do something like a chunked prefill, where if somebody like inputs a big block of text, say like 2048 tokens, that can be chunked up, and then we can mix and match decodes in there as well. And so it's really like flattened number of tokens is just like in aggregate, how many tokens are we processing at once? That's M. And that's much smaller and variable. Okay, let me pause. Are there any questions so far? Anybody want to, does this kind of make sense?
Yeah, I think we're good.
Okay.
Always roll back.
All right, thanks, Michael. Okay, so now we're going to look at some, performance numbers. So like what we're doing in this talk is we're saying we're interested in quantizing both weights and activations. And we call this W8, A8. So W8, 8-bit weights, A8, 8-bit activations. There are other things we could do here as well. So there's a lot of techniques where you quantize the weights, and often you can quantize to lower precision, in this case, stay to 4-bit, and then keep the activations at a higher precision. So, for example, on the right, I plotted basically gem performance for a large weight matrix. So we're fixing one large matrix. It's N by K, where both are 16,384 that I kind of picked arbitrarily. And then we're sweeping over M, the number of tokens, in powers of 2. And the thing you notice here is that, first of all, the kind of base BF16 torch matmul performance, it's, this is kind of like the baseline. You're not doing, performance will be, relatively lower. For low problem sizes, this Marlin W4A16 sort of does the best. In these cases, basically what this algorithm does is, the weight matrix is very large. It's 4-bit. It upconverts the weights from 4-bit to 16-bit in the innermost loop, of the gem, and then it computes in 16-bit. So you don't get any compute speedups over the baseline BF16 for this case, but you can get a lot of data movement savings. So most of the data that you process during this algorithm is in the weight matrix. And then the weight matrix is 4 times smaller than in the baseline case. And this turns out to work really, really well when your activations are small or you're processing very few number of tokens. In contrast, with activation quantization, this yellow line labeled CUTLASS FP8 A8 that we've implemented in vLLM, it does a little bit worse at a small number of tokens because the weight matrix isn't as compressed. But then as you increase the number of tokens, your arithmetic intensity increases, you have more compute to do, and so the rate of computation just becomes relatively more important. And so, what we found is that weight-only quantization is not sufficient for speedups in LLM inference, and you really want to quantize activations as well. Okay, now I want to spend some time justifying why in sort of like, like fundamental, I want like foundations of performance here. So I want to introduce, if you haven't seen it before, the Roofline model. So this is a pretty simple model. It's got 3 parameters. 2 of them are parameters of the machine that you're running on. So this is the rate of computation, which is, teraflops per second. So trillions of floating point operations per second. Another is the rate of data movement. So this is another machine parameter that's terabytes per second. And the third is arithmetic intensity. And arithmetic intensity is a property of the algorithm that you're running on the hardware. And that's in terms of flops per byte. So you can think of it like in a really simple case, if I have 3 vectors and I'm like adding 2 of them together, and then I'm multiplying them by the third, and then I'm writing it out, then I have to do 4, and like say each of them is an FP16. So then each is 2 bytes per element. So then you have to, you have 4 bytes, and then you do 2 flops with that. So then you have an arithmetic intensity of like 1/2. That's a really simple case. For matrix multiplication, you've got 3 operands rather, A, B, and C, and they're all n squared, where n is like the size of the matrix. As n grows, the amount of computation you do with them grows as n cubed. So the larger the size that you're working with, the higher the ratio of flops to memory operations is. So then the larger matrices you're working with, they have a higher arithmetic intensity. Okay, so let's go over to the roofline plot on the right. So here we're really plotting like one efficiency on the x-axis with another efficiency on the y-axis. So on the y-axis, we've got the performance in teraflops, which is like the achieved performance of an algorithm. And on the x-axis, we've got the arithmetic intensity, which is flops per byte, that's sort of like how efficient your algorithm is in terms of data movement. So you can kind of see as we, so this is, let me go back to the previous plot a second. So this, again, this is the same data as this. So if we look at this yellow cutlass line here, this corresponds to, the orange cutlass line here. So as we increase the M dimension, our arithmetic intensity increases and our performance increases as well. So fundamentally what the roofline plot says is, it says here are 2 upper bounds on performance based on a property of the algorithm. So you'll see like there are these kind of like 3 lines. So this blue line here is based on the bandwidth, which I'll get to in a second. But this horizontal line here, this is like the max compute you could ever do. We've got 2 lines just because there's a compute line, or there's INT8 computation and FP16 computation. Yes, hi. Would you like to please go ahead and ask a question?
Hey, Tyler. Good to hear your talk. So I have a very small question actually here. So it's great work. I see your Cutlass kernel reaching almost the roofline boundary, which is great. The question actually related to it is, because from early slide, the one slides before this, you have 3 curves, right? So I'm wondering, do you have curve for example, torch.compile for FP8? Because like, you know what I mean, right? So
yeah, I don't have it here. I have a plot with torch.scaled later in the presentation.
oh, cool.
Yeah, I do.
It's great.
Yeah. So the performance is like pretty comparable for most problem sizes. The difference is just like what you can do with it. It's Cutlass is going to be a little bit more flexible. I'll definitely get to that later.
Sure.
Yeah.
You're saying very close to your Cutlass kernel, right?
Yeah, it is.
Oh, cool. Yeah. Thank you.
Yeah. Okay. So the roofline plot. Let's get back to just like what this is, because I want to kind of get across like what the limit on computation is, and why, and like how this relates back to like the number of tokens we're processing. right? So these two horizontal lines, these are pretty easy. So here in red, we've got the max rate of computation, which is just like the rate that our machine computes at if you just have like pure INT8 computation or pure FP8 computation. And this green line is the same thing, but for BF16. And so the green line, that's the max that this Torch BF16 matmul could get. And the red line is the maximum that our Cutlass FP8 kernel could ever get. So that's sort of like one regime. Is at a high arithmetic intensity, you can hit the peak of the machine. When your computer when your algorithm doesn't do that much work with the data it brings in, it's more bandwidth limited. And the reason for this is really like, I have like a nice like thing written down. So like the bandwidth upper bound here. So if like beta is, if your machine can do beta terabytes per second, and your kernel can only do like X flops per byte, then like you will never be able to do more than beta times X flops per byte. Like it's basically a limit of like your algorithm is not efficient enough to like do that much work, because it just the ratio between like compute and data movement isn't high enough. So the thing that we see here is like, as the CMR increases, the Cutlass kernels kind of take off, but at low CMR, the weight-only quantization algorithms really win. Okay, so the arithmetic intensity really depends on M. But then there's a question of like, what values of M do we expect, right? So for prefills, we have sort of like really large M. So that depends on like, how much text is being inputted to the LLM at once. And so like you can see prefills of like, 1024, 2048, something large. Decode, especially a small batch size, will be, you'll have like one token at like batch size 1. Other things that affect them are like chunked prefill. So if you break up the prefills and mix them with decodes, then you shift from having some very long prefills to having like more medium-sized prefills and fewer really small, like small M decodes, basically. Speculative decoding, where you have a draft model, where you're just using the draft model to kind of speculate a few tokens and then using more prefills to validate them, can be used to push the number of tokens higher as well. So like, and then the other like really the largest factor is the QPS rate of the system. So higher QPS systems will just naturally have a larger batch size. And the other thing is like chunked prefill and spec decoding are really, these are tools we can use to push the arithmetic intensity higher in the future. So like I was saying kind of at the beginning of the talk before we really started, if you have a really small number of tokens, adding more tokens it's free in the sense that it doesn't add that much more data movement, and your data movement bound. It only adds more compute, and since you're not compute bound, it's like kind of free. So like that's why speculative decoding kind of like works really well in this case. The plot that we have here, this is from ShareGPT. What we really see is that we're not in a compute bound regime and we're not in a data movement bound regime. We're really in a mixture of both of them, which means that weight only quantization isn't sufficient for speedups, and you know, we need to quantize activations. We also need to get compression out of the weights, but it's not sufficient to only do that.
I believe this person is probably a Muslim and probably coming from a background because this person in particular always has.
Okay, so yeah, we're using Cutlass for our like W8A8 quantized operations. So yeah, first of all, what is it? So it's a library, or really as it, from their GitHub page, it's a collection of CUDA C++ template abstractions for implementing high performance linear algebra. So it's not like a library of precompiled kernels. They do have a library that you can download and use. Error builds, because I don't think they actually ship a binary. But it's really building blocks to let users like us build libraries from modular pieces that we use to construct specific kernels. It also has a layout algebra called Qt that's really nice, that formalizes sort of the mapping of like high dimensional tensor space to an offset in linear memory, and sort of like a formal algebra to think about those mappings. Yeah, and for vLLM, we see epilogue fusion as sort of the killer feature of Cutlass. So we're going to talk about that. So yeah, fusion is really like, it's a technique to reduce data movement by applying kind of like simple operations to operands that are already in fast memory, or as you're moving them into fast memory. And epilogue fusion is a specific kind of fusion where you're applying those operations to the output right before you write them out to GPU memory. This figure on the right, this is actually a CPU gem algorithm. This is Bliss that I worked on many years ago. Really, I want to use this picture as an example to say, like, look, any high performance gem is going to stage the computation by partitioning the matrices so that you're always working with a submatrix that fits in cache. And so here, we partition along this k dimension, and then we partition along n, and then we have this block that fits in the L3 cache of your CPU. And then we partition along m, and then you have this block of m that sits in the L2 cache. And then you multiply them while they are in cache. And then this figure actually first appeared in a paper where we essentially did fusion to speed up some like big O of n squared operations that come up when you implement a complex matrix multiplication in terms of some like real multiplications. Epilogue fusion, as it turns out, kind of like works really well. It's kind of like the easiest, most efficient place to fuse. That ends up being the case because you can simply, let me go back. While the output is still in registers, you can apply operations to it. It's very small, so like these are essentially free. You're not even loading them from cache. And then, you only have to do it once, essentially. So if you say fuse into, you can do other things, like you can do input fusion while you pack this sub block of A into the L2 cache. The downside there is you actually have to do this multiple times because this block will be used multiple times because it will be used for every B here. So epilogue fusion turns out to work really nice, and Cutlass supports epilogue fusion, just doesn't support any kind of input fusion. Okay, so now let's talk about like symmetric quantization and like what we do during the epilogues. So if we have a symmetric quantized gem, we're multiplying x times w. W will be quantized as s sub w times w hat. W hat is the quantized version of w, s sub w is the scale of w. And then similarly for x. All right, so then if we multiply these together, we can just commute our scales. We can perform this quantized gem, x hat, w hat, and then the scales happen on the outside. And what it means to happen on the outside is we apply them to the output while they're in registers or in shared memory right before writing them out to GPU DRAM. And the important thing here to see is that there are multiple cases that we have to handle here. So we can have per tensor, or per channel, per token, or per tensor, per token. We could maybe even have per tensor, per channel. And then these S sub W's times the output, yeah, these happen during the Cutlass epilogues. 0 points are a little bit trickier. So asymmetric quantization adds a 0 point where, instead of just having a scale, we have x minus this term here. So at z sub x is that's our 0 point. This circle is it's an Hadamard product, so that's just an element-wise multiply with broadcasting, and then j sub x is just a vector of all ones, or a matrix of all ones. So we can do a little linear algebra and rewrite it as the following. And for the static per tensor case, we just have this vector that we pre-compute ahead of time that needs to get added during the epilogue. The dynamic per token case is a little bit more complicated, where we can't totally pre-compute this because this z sub x becomes a column, and then this j sub and then this j sub x w hat becomes a row, and then we end up having to do an outer product during the epilogue, or we have to do an outer product to compute the term. That would be very large if we pre-computed it ahead of time. And we also don't know the scales ahead of time in the dynamic case. So then we just do this outer product during the epilogue. And the nice thing about Cutlass was this actually turned out to just work, which was really nice to see. Okay, so now, hi, you asked about torch.scaled.mm. So yeah, here you'll see basically the effects of epilogue fusion. So yeah, we're appending computationally cheap operations onto larger operations with very little overhead. The thing that I want to show off here is less the comparison to torch.scaled.mm and really the comparison of our per tensor Cutlass gems versus the per token per channel gems, where they basically lose no performance by going to per channel or per token per channel.
Yes, thank you.
Yeah, and then so in 2.4, PyTorch 2.4 scaled.mm doesn't support the scales to be vectors. So they will in 2.5, but that's not out yet. So in 2.4, if you want to support per token per channel, what you have to do is you have to wrap the operation. You have to basically do the gem and then post-process it afterwards with like separate operations. And this turns out to be very expensive. So we lost so this right here doesn't have coup de graphs or torch.compile. vLLM does use coup de graphs. Where we do this as a fallback, you do lose about like 25% performance end to end using torch.scaled.mm in this case. One last like nugget. I don't know if we have the Cutlass team on at all. I think they might have joined. One last thing we did in vLLM was we saved on binary size and compilation time by keeping the kernel small. So yeah, vLLM just tries to keep the size under 250 megabytes. The thing about Cutlass is since it's C++ templates, you might get a combination. You like tend to get a combinatorial explosion of kernels generated. So one of the things we did was we implemented custom Cutlass epilogues to do the per token and per channel with the same code as the per tensor case, which gave us like a 4x savings. We also like implemented these little shims to like wrap our kernels and like basically turn them off on architectures that we're not going to use them on to save even more. Yeah, and then so here's some end-to-end numbers. So on the right, and the thing I want to say here is like we put all this work in for, specifically to handle like asymmetric quantization, to handle, per channel, per token quantization. The first model where we actually needed this for FP8 was Metalama 3.1405B. And so it happened that because we put in all of this work, really with an eye on INT8 quantization, it meant that we already had everything we needed in place for FP8. So we kind of, some combination of like, we were really prepared / we got lucky. This also happened to be the first model where in vLLM where we needed to skip some layers for quantization, which is something we've run into before for INT8 quantization. And then, yeah, on the right, you can see as the queries per second increase, end-to-end performance kind of switches from a really low QPS. Your gems are, really small M, really small number of tokens, bandwidth limited, and your weight-only quantization kind of wins. But as you increase, you kind of start to, look at the W8A8 sort of starts to dominate. I will say that this kind of, ultimately you want both, right? So we're looking at W4A8 as well. Okay, so that's about everything. So yeah, what's next for vLLM plus Cutlass? Because we have future plans. So we're working on some future Hopper optimized Marlin style mixed precision kernels. We're also working on some fused gems plus all gathers and reduced scatters. Integrating some ByteDance kernels that are also Cutlass based into vLLM. And then further down the line is we're thinking about, but not quite on the roadmap, is fused MOE Cutlass based kernels. And I'd also like to thank the other Neural Magic team members who helped with this talk or helped with the Cutlass kernel implementations of Lucas Wilkinson, Varun, Rabindranath, and Luka Govic. All right, so that's it for me. So back to you, Michael.
Yeah, thanks a lot. We had lots of questions in the chat, so definitely feel free to look through them yourself. Can you stop sharing so I can take it? But I think we got to a lot of them, so yeah, really happy to see the interest. So let me switch over for the rest of the stuff. We're running a little short on time, so thanks for being patient with us. I'll try to get through my stuff a bit quickly so we can go through the rest of the questions. So first, just want to talk about if you're interested in like producing or getting your own like INT8 or FP8 models with activation quantization. We've done a lot of work in making LLM compressor under the vLLM project with relatively easy to use interfaces for weight-only quantization, activation quantization. So like here are some examples of how easy it is to produce your own models. Go check out the project or the docs on the vLLM docs website for how to make use of the FP8 and INT8 quantization that Tyler talked about. I'll quickly go over what's new in the vLLM releases. There's a lot to go over, so feel free to ask questions on specific things. Basically, there was a lot of model support, so like Jamba 1.5, Ultravox, which was important as the first audio model. There's been a lot of continuous improvement on vision language models. We actually added support for GGUF models, expanding support and actually making it so you can start to serve encoder-decoder models, and additional work on speculative decoding. There's also been a good bit of work on TPU and Intel CPUs for more hardware support there. And then some of the performance improvements that we'll go over later. But most namely, we've been working heavily on multi-step scheduling, which, I'll go into more detail later on. And mostly like in terms of new features or things you can use, there's a new like chat method on the offline LLM class, so you can easily do like chat templating and easy prompting for instruct models within vLLM. And there's a good bit of like continuous work on torch.compile, I think, between both of these releases. So jumping to 0.6, which just came out late last night or early this morning, depending on where you're at. This is really where we considered like a really good stopping point for the performance improvements on vLLM. We've been working for over a month. We'll go over the blog right after this. But essentially, multi-step scheduler is a lot more stable and able to be used. There's still some things that it needs support for, like pipeline parallelism and various other things. But please feel free to test it and report any issues, as we definitely want it to improve the feature matrix for it. There's also been a lot of good work. I think actually NVIDIA helped out on this in terms of utilizing the flash infer backend for FP8 for like accelerated FP8 KV cache. Fusing onto the still unquantized attention, but seeing some performance just through compression of the KV cache in those memory bound regimes. And then a lot of work on expanding hardware support. We added AWQ for AMD GPUs. We did some tuning on NVIDIA GPU, or tuning for H200 NVIDIA GPUs. Intel GPUs get additional support, including pipeline parallelism, so you can deploy across nodes. AWS Neuron, so Inferentia specifically, has been getting a good bit of work as well. And a lot of work on TPU, continuing to make that a good hardware choice. Then in terms of model support, we greatly expanded support for bits and bytes models. So pretty much any type of bits and bytes checkpoint that's out there on Hugging Face now should be able to be loaded and run in vLLM. Various models got added, EXO1, which was a Korean language model, Granite, which is a model from IBM, and Feed 3.5 MOE, which is a very capable small MOE from Microsoft. Mistral has been contributing fixes for to get accurate tokenization for their models. And as I mentioned before, a lot of additional work on improving vision language models, and particularly trying to expand outside of just single images, and expanding into audio as well. A really big feature that's been in progress for a while that I helped shepherd was the tools API for the OpenAI interface is finally in, thanks to Kyle, who's been coming to these talks for a while now. Another big feature is chunked prefill and prefix caching can be enabled together. This is a big feature for people who want to use shared long prompts in their requests. A lot of progress on torch.compile as the vLLM team has been collaborating with the PyTorch folks to get towards end-to-end torch.compile enablement on the PyTorch nightly. Just blasting through things. Feel free to keep putting in your questions. I'll stay on to talk to anyone who wants to talk on individual questions. But we definitely want to talk about the big release of 0.6 and the blog that went out this morning on the improvements vLLM has had over the past several releases, really over just like a month or two. So the numbers speak for themselves. We've, multiple times improvement in throughput and latency and in high load scenarios, and really bringing vLLM, at the very least up to par with other, great inference servers like SGLang or TensorRT LLM. Mind you, all this is at, FP16, bfloat 16, no quantization involved. But, as you bring in some of the quantization methods we've worked on in vLLM, the performance will just get better from there. And so one of the things I want to talk about is some of the improvements that, contributors have been working on. One of the key ones was sort of the realization that, a lot of things in vLLM, once you get under load, are sort of CPU bound because we have so much Python code and a lot of like async IO usage. So this really sort of impacts whether you're on a fast CPU or a slow CPU. So we did a lot of things to cause less, contention of the global interpreter lock in Python. One of these key things that Rob Shaw from Neural Magic worked on was separating the API server, which was dealing with HTTP requests and not really performant things, separating this from the vLLM engine so these things can run in separate processes and can just do message passing and aren't fighting for the same CPU thread over. That was a big one. Another key one that we mentioned before is this batch scheduling multiple steps. So this just means that, as we're trying to schedule new requests coming in or requests that are finished and need to get pulled out of the GPU, we can schedule n steps at once. So we need less synchronization with the GPU, and we can spend more time doing forward passes and getting good utilization of the hardware. This greatly increases throughput and, it generally reduces the latency from synchronization, particularly in, tensor parallel scenarios. Another big thing was asynchronous output processing. So before we would essentially, once we've done a forward pass on the GPU and we needed to process the outputs, decode tokens or check if we're done with work, we would pause the GPU while looking at this. Now we allow for asynchronicity between this, and in sometimes we get a little bit of wasted work on the GPU. But the most important thing is that this really improves efficiency of the GPU, so they don't need to. There's less synchronization they need to deal with, and definitely improves throughput scenarios by a lot. So those are some of the three major things. Make sure to check out the PRs. But most importantly, definitely check out the blog to get more information on all the changes there. I think we're right at time here. So definitely understand if you need to leave early, but I'll go through some of the questions that were asked ahead of time and in the chat, and if anyone wants to speak up or ask questions here, this is definitely your time. So the top two are basically the same. There's been stability issues on the main branch. This is definitely something that annoys all of us. Part of this has been introduced by adding conditional testing. So we don't run all the tests on every PR. They're run basically whenever, we detect that a test is likely to be affected by changes to certain parts of the code. This has definitely helped reduce CI costs because they're really high. It's really great that we get to run a lot of GPUs on every PR, but it does cost the project quite a bit. We're still figuring out the right balance for this. Definitely one of the main things that contributors have set up last week is starting to set more accountability for who's responsible for making sure what tests are up and green. So we're basically instituting named contributors responsible for upkeeping certain tests. So this will make it very clear if a certain test is failing. We have a short list of people to call and who can look into it shortly. So we definitely expect that to improve. The third question, how can you use your libraries to train low precision, high speed models? Basically, LLM compressor is what you want to look at for quantization of these models in a variety of different schemes. And that's also under the vLLM project. So check it out on GitHub. On this fourth one, brief overview. The capabilities, there's obviously a lot of them. If that person could step up and ask for something specific, that would be great. Justin, you have your hand up. Okay, I'm gonna.
Hey, sorry, I couldn't find the mute button. Yeah, I just had a couple questions. First of all, I've been using the LLM compressor. Thank you so much for open sourcing that. It's incredible work. Question on that is in terms of quantization, do you see an effect where maybe the calibration data set that you're using is too large, if that affects the quality of the quantization? The hypothesis that I'm working on is if you give it too much data to quantize, it views all the weights as being important, and then you don't really get much benefit over a static quantization. Is there any truth to that statement?
So you're saying this is like the data used for calibration?
Yeah.
Yeah. I'll say it's definitely a tricky thing. I mean, there's not a lot of harm in adding more calibration data. I don't think it's really going to hurt your accuracy, since I mean, it's kind of good to like weight everything and understand how all the weights or activations are important and important to the loss. Yeah, I mean, really kind of the simple rule is like as much tokens you can use, for whatever budget you have for quantization, is probably not going to hurt you, except in like really extreme scenarios where you're using GPTQ and with a lot of tokens, in a very specific domain might hurt you, and it might overfit on those specific domains. But if you're looking for a general model and throwing a lot of general data or even random tokens at it, that can help overall performance.
Okay, yeah, that's good to know. Thank you. And the second part to that question is, as far as generating that calibration data set, do you have any examples or tips and tricks as to what you've seen works best in terms of those calibration data sets?
Yeah, definitely, using samples with a lot of tokens are useful, rather long token lengths are useful. You don't want to use a bunch of sort of short token examples. This can really hurt you once you start trying to use your whole context length, particularly for methods like GPTQ, where you're updating the weights. Yeah, I mean, sort of the main things are making sure you have a good distribution of the domains that you're interested in. If you're just specializing for math and code, you can specialize on those data sets. But if you're trying to, produce like a generally useful model, you need to include some chat data, some math data, some code data, some philosophy data, or even random tokens. And mostly, the best resource for this are fine-tuning data sets that are openly available. Those high quality, state-of-the-art fine-tuning data sets are usually some of the best tokens you can get in terms of bang for buck for your token budget for calibration.
100% agree. I guess I was trying to get at more like, does the format of the format of the prompt that you're giving it matter so much when you're quantizing, or should that match really exactly what you're trying to do with the training and the schema?
Yeah, I mean, it should match how you're trying to use the model. So for instance, if you're like using like a llama instruct model, you very much should be putting your prompts and putting your data in like the chat templating that model uses. There's some papers on this that I can't pull in right immediately, but especially having some of these important bits of the tokenizer, like the beginning of sequence token or the assistant or user tokens. These are these sort of like pivot tokens that delineate different parts of the the text that you're working with are really important.
Sounds good. Makes sense. Thank you so much. Appreciate your help. Appreciate all that you're doing here.
Yeah, great. Yeah, there was another question on running vLLM with MLflow. If anyone is here to talk directly on that, happy to do some back and forth, but I don't know anything that would make it specifically inefficient with MLflow. We deploy vLLM a lot, maybe at a more raw level with Kserve and Kubernetes autoscaling. So that's definitely more, as I understand it, bare bones compared to MLflow. But vLLM is ultimately like a Python package with optimized binaries attached to it. So you should be able to infer with it and build things on top of it as you will, either at the Python level or on the API server level using the OpenAI API.
Hi, yeah, thank you for that answer. As is actually my question.
Okay.
So maybe for some more context, I feel like I may be using vLLM in like an unconventional way, just because my org is kind of in a like preliminary phase trying to optimize like LLM inference times. We're like very entrenched in like the Databricks environment, and like I'm kind of unable to get like GPU or like VM compute, like specialized compute allocated for like serving open source LLMs. But I do have the ability to create serving endpoints in Databricks, which like gives you access to T4s and A100s. And like the like method I've been using is like creating like a PyFunk wrapper for like a model using vLLM, like, and then registering the model in MLflow, and then serving that at a Databricks serving endpoint. I was just really wondering if there was any perspective like you guys might have about this process. Like, is this going to add latency no matter what? Like, or does this like really limit the ability to demonstrate optimized inference?
Yeah, I mean, ultimately, if you're able to like, define Python classes and functions and like register them, like you probably won't be able to use like the API server like as it is, but you absolutely can use like the async LLM engine, which is what the OpenAI API server like builds on top of, and get access to the same backend and asynchronous scheduling that offers. Yeah, definitely maybe going to be a bit involved, but yeah, I mean, happy to talk and connect and like learn more specifically about like what interface you have available. I think we have a few instances internally of helping people make their own front-end wrappers around the async LLM engine because they can't use like the OpenAI server, for instance.
Okay, so yeah, I would love to reach out about that because I'm actually, I found a workaround to run the LLM engine, but not the async engine, and I was not sure how much time to think into that.
Yeah, definitely. Yeah, feel free to send an email at Michael@NeuralMagic, and yeah, we can talk.
Okay, thank you so much.
Daniel, you have your hand up.
Hello, is it working?
Yeah.
Okay. Yeah. Just hello. I don't really have a question, but like just hello from Onslaught. We really appreciate the work.
I know you're the Onslaught guy.
Yeah. So just wanted to say like great work on the new version. The open source community is extremely excited for that. Chunk prefill plus prefix caching. That was a very big request. So great work. And also like LLM compressor, great work on open sourcing that. That's very cool. So yeah, I just wanted to say, the open source community loves your, like everyone's like, you guys' work. So like keep up the great work. So not really a question, just wanted to say great work. Yeah.
Cool. Yeah, no, appreciate it. And Onslaught is definitely a great project for fine tuning efficiently. So check them out if you're interested in that. Yeah, I mean, actually in LLM compressor, we're like mostly focused on post-training compression at the moment, but we absolutely have like some flows in there for like training aware compression or like sparse fine tuning from some of our older research. So we have like a TRL like integration, like we can like hook onto like a HF trainer. And so we have some examples working with TRL that yeah, it would be cool to like get it working with Onslaught too, to like, yeah, make it quite a bit faster. Yeah.
Yeah, more than happy to collaborate as well. But yeah, just great work. Keep up the fantastic work. Yeah.
Cool. Appreciate it. Definitely feel free to pop in with other questions, but yeah, there's a few more questions here. So yeah, what params can you tweak for better throughput when serving? Definitely, you know, I think in terms of throughput, you want to like tune like the maximal GPU memory utilization that you can. So you're making as much space for KV cache so you know, for running like multiple requests, batching multiple requests in parallel as possible. Definitely, you know, enabling chunked prefill, so you can get better like output token throughput and get less interruptions from you know, prefill interrupting your decode times. Also, like particularly for 405B, it can be better even if you have enough memory to split up and use pipeline parallelism to split across multiple nodes, in order to get better throughput and more space for KV cache, better batching as well. You know, don't just think about tensor parallelism, also think about pipeline parallelism, particularly for request throughput. And activation quantization, more flops, better, you know, more memory usage, but really when we're talking about request throughput, yeah, using those INT8 or FP8 tensor cores would, you know, has the potential for a 2x boost over using, you know, FP16. And this last question is a big one, but it's kind of a topic we've had asked before. So basically just like running multiple copies of vLLM on a single GPU. So yeah, you know, vLLM by default, when you're running it on a GPU or a set of GPUs, it is going to assume that it has all of the resources of those GPUs for itself, and it's going to, you know, pre-allocate all the memory for the weights and the KV cache in order to have efficient serving. But you can like control and lower this GPU memory utilization parameter to say like maybe 40%, and load like 2 models at 40% utilization on one GPU to fit it in. And yeah, you can get this as low as you want as long as your weights have enough space too. And that's going to work. Yeah, so that's basically what you should do here. And I think, you know, whoever wrote this has the right idea. And I think that's basically it. So there's a question from Ed Sealing, calibration data question. If you created the data set from the non-quantized version, would that improve performance? Yeah, definitely. You know, we've done a good bit of experiments with distillation. We've done this more for more like training aware methods or like you know, making synthetic data sets and you know, maybe sparsifying a model and then trying to retrain it, you know, with some sort of distillation loss with the original model. I don't know if like creating a data set is really going to be useful here. Really, in terms of like the calibration for most use cases or for most algorithms, just getting a good variety of representative tokens that you're going to use in the model is the most important part versus like tokens that the model produces so much, since during calibration, you're not doing any generation, you're just doing, you know, the forward pass for the prefill. Okay, Steve, you have a question?
Yes, I have a question here. Last week, or 2 weeks ago, when we had the last office hours, it was mentioned that if you have AMD and you want performance, to use their fork. And I was curious, how close are they to completing their support?
Yeah, so it depends on a few things. I think there's like some specific features that AMD has in their fork that maybe have like less of a chance of landing in the main fork. For instance, you know, mostly from like a usability perspective, for instance, I know like the AMD like ROCm vLLM fork has these like tuned FP8 gems, or maybe also unquantized gems, that essentially take a long time to like do all of the tuning and do all of the like the grid search of matrix multiplication parameters at runtime. This isn't really something we want to have in vLLM. Like with things like Cutlass, we do like more offline tuning and set up heuristics in the project, and we we don't do any like compilation at runtime for gems like that outside of Triton or like torch.compile. So there's some things like that. I don't think there's a lot of like performance features, so to speak, or like different like system level optimization features. I think with the ROCm fork, it's mostly like, using like the nightly version of ROCm with like the nightly version of PyTorch that supports it. So it's a very like fast moving and sort of bleeding edge work that like they're working closely with the PyTorch team on, or their internal like driver teams. So it's just a bit less stable, but of course, because they're like working on improving it, it is going to be the highest level of performance that they can offer and that they're working on. I still think like, particularly given some of these CPU performance improvements, I think the performance of AMD GPUs on upstream vLLM is definitely going to be quite a bit better as well. For some specific features, it's going to be a bit complicated. My best recommendation there is to open up an issue on the ROCm vLLM fork and ask them directly there. They're usually pretty responsive.
Okay, all right, that's a good idea. Also recently in the 0.55 release, it's starting to ask for chat templates. And I was wondering if you could elaborate a little bit on why it now actively asks for chat templates when certain models didn't require one before.
Yeah, so that's actually not something that we require in vLLM. That's something Transformers now requires. I think with like Transformers 4.40 or somewhere around that, they introduced this breaking change where they're not going to. So essentially, before they would like default to some sort of chat template for models that they couldn't find chat templates for, and this is in most cases like bad behavior for models that just like don't have chat templates. Like you just either like should not ever use a chat template with a model that hasn't been trained on one, or get the right one that's registered for the model and its tokenizer. This shouldn't block you from using the model. It should be more of like a warning, and is a valid warning that you shouldn't use like the chat API or the chat endpoint on the OpenAI API, because that requires using a chat template. And you should stick to just using the completions API, which doesn't do any, chat templating. If it's blocking you, definitely open an issue. We don't want that to be a blocker. We definitely want you to be able to use models that don't have a chat template. But this is unfortunately something that Hugging Face pushed as a breaking change. And you can maybe get away with it by downgrading transformers, but there might be other things we depend on in vLLM for, having those more modern versions of transformers, particularly like recent model support.
Yeah, we found some Python code that is testing and blocking if you don't have one. But we were also testing models like GGF format, which has in the metadata a chat template. And we were wondering, if that chat template could be extracted at runtime, as opposed to having to hand a specific chat template separately.
Yeah, that I think that totally should be. The GGF support is really relatively new. It like landed without like tensor parallelism support, although we added this just recently. I think as much as possible, if you can open up issues for some of these things or are willing to contribute them, that's definitely welcome. GGF is just like early, especially. So there's definitely some, user experience that can be improved there. I think that's definitely something that's tractable.
Okay. All right. Well, thank you very much. That's all I have.
Cool. Cool. Appreciate it. So definitely feel free to anyone else like hop up with questions. Thank all you people for sticking extra as we go way over. But definitely to close out, please, contribute to vLLM, open up issues. If you want to work on things you're not up to speed on the project, look for some of the good first issue tags, or just search for things that you're interested in, like speculative decoding or torch.compile. We're always looking for more people to join the projects that we're working on or leading. Definitely give us feedback right here or on the Discord for office hours or anything else that vLLM could do better. We know we always need improved docs, but it's useful when people call out on specific docs that need to be written. And there's a lot of upcoming events where either the UC Berkeley folks at vLLM or Neural Magic folks here will be at, particularly like AI conference and Race Summit in San Francisco, and NeurIPS is always a great time in December. And yeah, if you liked any of the stuff we talked about, or especially are interested in making fast inference possible, Neural Magic is hiring people to work directly on vLLM, and particularly, always hiring talented systems engineers or HPC engineers. So definitely feel free to look at our jobs or reach out to me directly, michael@neuralmagic.com, and let me know if you're interested. So I think that's basically it. Thanks everyone for taking time, and yeah, the slides are in the chat, and the recording should be available in 2 days, maybe like Monday next week. I'm not sure. Yeah, that's it. There's one last question from Aditya. How does Samba Nova and Grok chips work, and will that kind of hardware be in our hands? That's a question for the hardware providers, whether the hardware will be on your hands. Yeah, I think I don't think we've heard anything from like those specific hardware providers like wanting to make a backend into vLLM. Considering they're like really specialized hardware, it may be difficult for them to like be like really like PyTorch friendly, which is what we aim for in vLLM. Yeah, and I definitely think like Grok and Samba Nova are not the kinds of the companies that are gonna like sell like PCIe cards that you can like plug into your local computers. Maybe if you get a nice data center deal going. But yeah, I mean, if you're interested in contributing a backend, definitely open to it. But yeah, that's to be determined on those ones. Okay, we've definitely gone long enough. Thanks everyone. Take care. Hope you enjoyed the time. Have a good week.